Alright, so this second video is going to focus on rate laws and how we determine rate laws depending on the type of data that we're given. Your rate laws are not necessarily going to match up with the stoichiometric ratios in your balanced equations. They have to be determined experimentally, and you basically, just like any good scientific experiment, have to vary one of your reactants and see how that affects the speed of your reaction. How would it change the rate of it? Because the reactants are going to be what determines how quickly the reaction proceeds. Based on the graph, we only include those in our rate law expression, and our rate law expression will include the rate, and it will set it equal to a constant K. That rate constant is specific for a set temperature for that reaction, and it's basically just looking at the slope as to how quickly that reaction proceeds, times each reactant's concentration raised to an exponent, telling us whether it's a direct relationship, it's more of a squared relationship, or maybe the reactant isn't involved at all, and so it would have an order of 0. We use initial rates, basically what happens right after the reaction first gets going, to determine these rate laws, and so we will also need initial concentrations. We can find the overall order of our reaction by adding together the exponents of all the reactants that are present in our rate law expression to get the overall reactions order. So the example I have down here, we have 3 reactants, H2, SeO3, H+, and I- that are combining together to form the products. We see that H2, SeO3 does not have an exponent because its order is 1. It's a direct relationship. H+ has a squared relationship with it, so it would be an order of 2. And I- is raised to a factor of 3. Its order would be 3, so together the individual orders when added would give us the overall order of 6. And that's just telling us basically how many and in what level the reactants are affecting the reactions rate. Now bear with me because I know you're like, what the heck is she talking about? We're going to go through and explain how you would get an actual rate law expression with data. All I'm doing on this slide is just trying to introduce you to some of the vocabulary. So here's another example. You've got the rate law for this reaction. Chlorine and chloroform makes HCl and carbon tetrachloride. And you're told the rate is equal to K times chlorine's concentration squared times chloroform. I want to know the orders of the reactants and the overall reaction order. Well, chlorine is raised to an exponent of 2, so it has an order of 2. Chloroform is not raised to any specific exponent, so its order is 1. Anything to the 0 would not be written, so if you did not have a reactant included in your rate law expression, you could assume its order is 0. And the overall order would be the 2 orders added together, 2 plus 1 giving me 3. To find your units of K, it's going to depend on how the reactants are affecting your rate law. And so the K's units are going to vary depending on how many concentration units are affecting that rate. We are told to assume the rate is in molarity, or concentration is moles per liter, and the time is in seconds. So if we take our rate units, it would be concentration over time. And if we look at our rate law expression, that would be the units molarity per second that we would substitute in for our rate. K's units are what we're trying to find. Chlorine's units are going to be molarity, but because there's a 2 that it's raised to, they'll be molarity squared. And chloroform's units, there's nothing chloroform's raised to, would just be molarity. So if I'm just looking at units without any numbers, the rate's units would be molarity per second. The concentration of chlorine would be molarity squared because of its order, and the concentration of chloroform would just be molarity. So together that gives me molarity cubed. But to get K's units by itself, I would divide both sides by molarity squared and molarity. One of the molarities cancels out on the left side. They all cancel out on the right side. And that leaves me with molarity squared in my denominator. And second is also in the denominator because it's underneath the division sign of molarity per second. So K's units would be 1 over molarity squared times second, or molarity to the negative 2 seconds to the negative 1. And we'll do some more of those, so if that threw you for a loop, hang in there. We're going to go through a couple more examples. One way we can determine the rate law is looking at how the rate of the reaction varies depending on the concentrations that are present of our reactants, and that's what we're going to do in these first couple of examples. We have I minus and S2O8 2 minus combining to make iodine and sulfate ions, and we are looking at the rates based on the decrease in S2O8 over a period of time. That's where these initial rates came from. And we have the concentrations of S2O8 initially, as well as I minus, our two reactants. So we're going to determine our rate law and calculate our constant, and then we're going to determine what would be the initial rate, this value over here, if we had two different concentrations for our reactants, 0.060 molar for I minus and 0.015 molar for S2O8 2 minus. So the first thing we want to do is to find a pair of reactions where I minus is changing, but S2O8 2 minus is staying constant. If it's staying constant, it can't affect the rate, and we can remove it from our calculation to solve for the order of I minus. So for I minus, if we look, we see that the first two trials, 1 and 2, I minus is changing, S2O8 2 minus is constant, and our rate is changing as well. So we just want to have it that one reactant's changing while the other one's remaining the same. I always set these up so that the one with the higher concentration is in the numerator, and the one that is in has a less concentration would be in the denominator. So if I take my rate law expression, rate equals K times the concentration of each reactant raised to their order. This would be the concentration of I minus for the first experiment over I minus for the second. S2O8 got canceled out because it's the same concentration. And now I can look at how the rate is affected. 12.5 times 10 to the negative 6 over 6.25 times 10 to the negative 6. You may be asking where K went. Remember, it's rate equals K times these concentrations. Well, if you have a K in the numerator and the K in the denominator, they're going to cancel out. So that's why we don't need to worry about including K. The only thing that's truly changing is the concentration of I minus, and we're going to see how it affects our rate. 0.08 over 0.04 is 2. So 2 to the m is equal to 2 as well on the right side of our equal sign. And the only way you can get 2 to equal 2 is if your order m is 1. So that tells us the order of I minus. And now we're going to look at S2O8 2 minus. Again, we want to find two reactions where S2O8 minus 2 minus is changing and I minus is staying the same. So if I'm looking through my reactions, it looks to me we might be looking at 1 and 3. Because we see in 1 and 3, I minus stays constant, while S2O8 2 minus changes. So because I minus is constant and our rate constant is also constant at a given temperature, we're not going to include those when we compare the two rate laws to one another. We're just going to include S2O8 2 minus's concentration, again the larger one being first, 0.04 to 0.02, and we're going to compare it to those two rates, 12.5 to the negative 6 and 6.25 times 10 to the negative 6. 0.04 over 0.02 still gives me 2. 12.5 over 6.25 also gives me 2. So 2 to the n would equal 2, and the order of S2O8 2 minus would be 1 as well. So the rate law that we want to rate would include the constant K and each of our reactants raised to their orders. These were both orders of 1, so it's just K times I minus's concentration times S2O8 2 minus's concentration. Now we have 5 sets of data here, and to find the value of K, which is the next part of our question, we can take any of these 5 sets of data as long as we use everything in that row to calculate K. K is a constant, so it shouldn't matter which set of data we take. We should get roughly the same value for each set of data. So if I take the last set of data, 7 times 10 to the negative 6 molar per second, I plug that in for my rate, I leave K alone, and I substitute in my concentrations when the rate is 7 times 10 to the negative 6, and I go through and solve for K, I get that it's 3.9 times 10 to the negative third. You have 2 molarities over here, so when you divide them into the left side of the equation, only one cancels out, which is why we see 1 molarity and 1 second left as our units. the -1 is telling us they are found in the denominator. And the last thing we're going to do is take the rate law expression now that we have, rate equals K, which we now have, 3.9 times 10 to the -3 molar seconds, and we're going to substitute in those concentrations that I gave you back at the beginning of this problem, 0.060 molar and 0.015 molar. One of the molarities cancels out, and that leaves us with molarity per second, and those are appropriate units for rate, so we should be good there. All we have to do is multiply, and we get that the rate of that reaction that we had not tested yet should be roughly 3.5 times 10 to the -6. Okay? And this is why I wanted to review your data when we did this lab, because I just wanted to make sure that when you were comparing your reactions to one another, your data was reasonable. Now, everybody else had one other example to do for homework, which is the next one coming up. You guys weren't here for this, so I'm going to go ahead and do this last example. And it involves chlorate and chloride ions and hydrogen, making chlorine and water. So this time we have 3 reactants. So when we pick our experiments, we want to vary one of the reactants at a time, leaving the other 2 alone, and see how they affect the rate. So we're going to find the orders for these reactants, the reaction order overall, and a rate constant K. So if I look for ClO3-, it looks to me like, looking to see which one would be appropriate. 0.04, 0.04. I don't know if we can find ClO3 with this information. Oh, maybe there's one there. Give me a second. We're going to use the first one and the last one. I see it now. Sorry, because the first one we see ClO3 going from 0.2 to 0.4, but we see Cl- staying at 0.2, and we see H+ staying at 0.2. So only ClO3 would be changing, and we're going to see how it affects the rate of the reaction when ClO3- is doubled. So when we compare the rates, again, I'm taking the one with the greater concentration, putting it on top, 0.4 over 0.2, and I'm setting that equal to the 2 rates, 3.2 to the -3 and 1.6 to the -3. I see that 0.4 over 0.2 would give me roughly 2, and as well as 3.2 over 1.6. So 2 to the m equals 2, so the order of ClO3- would be 1. Next, I'm going to look at finding a pair of reactions where Cl- is changing and the other 2 are remaining the same. And it looks to me like that's going to be 3 and 4. We see that Cl- is roughly doubling between 4 and 3, but ClO3- and H+ are staying constant. So as we compare the rates, the concentrations of Cl- from 3 to 4 and the rates, we see that they both are roughly doubling. So again, the order is going to be 1. Again, this is not always the case. We are going to have reactions that are going to have orders of 0. We're going to have ones that have orders of 2. And you could have an oddball reaction that has an order of like a half. Okay, so then the last one we're going to look at is H+. Looks to me like experiments 1 and 2 are going to be appropriate to use to look at H+, because ClO3- and Cl- aren't changing. So if I compare H+'s concentration, again, the higher one on top, and then I compare it to the rates for experiment 2 versus experiment 1, I see this time as the concentration doubles, the rate roughly quadruples. And so if I solve for P, I get that the order of H+ for this rate would be actually 2. So my rate law expression would have 1s for the chlorine containing reactants and a 2 for the hydrogen ions. So if you have set your rate law up correctly, again, you can use any of the 4 experiments to find the constant K. I do think I asked you for the overall reaction order, so we're just going to take each of the individual reactants, 1, 1, and 2, and add them together. And then to solve for K, I picked the first experiment this time. I substituted in my value for the rate, as well as the concentrations for each of the reactants in experiment 1. This time I'm going to have a molarity and a molarity and a molarity squared, which would give me molarity to the 4th. Only one of the molarities will cancel out, leaving me with molarity to the -3rd and seconds to the -1 as my units. And when I do the math through, this gives me a value of 1. Okay, so that should be the end of your differential rate law examples, and let me know if you have any questions.